Hello everyone, welcome back. This will be Fluid Mechanics Homework number 2, Part B. So let's get into it. So Part B is only one part, and its problem statement is asking, using a force balance on a rectangular prism, demonstrate that the buoyant force is equal to the weight of the fluid displaced. Explain how this extends to an arbitrary shaped object, for example, a human body. So the first thing I'm going to do is I'm going to draw a diagram of our rectangular prism. So we can imagine we have some sort of tank here, and we've lowered our rectangular prism in. It's connected to a rope, and it is fully submerged in a liquid, or a fluid, sorry. And we're going to give our rectangular prism a height of big H, and it will be of depth small h down. So, we are trying to figure out the buoyant force of this object, and we're trying to demonstrate that the buoyant force is equal to the weight of the fluid displaced. So there are going to be pressure forces acting on our rectangular prism, and the pressure force acting on the bottom of a rectangular prism will be going up, and we're also going to give our rectangular prism a cross-sectional area of big A. And so we have this acting on the bottom, which is at depth small h plus big H. And this in the top of our rectangular prism is at depth h. So the force going up, acting upward, is a pressure force. And we know pressure forces is pressure times some area. Or it's also, it's at a different depth, so it will be rho gh. So it is the density, and let's call our fluid H2O in this case. And we're going to make our bar gold, so AU. So it will be the density of H2O times the gravitational constant times the depth of H plus H. And then we need it to be a pressure force, so times it by the area, cross-sectional area A. So this is the force acting on the bottom of a rectangular prism. Now we need to find the force acting on the top. So the force acting downward, in this case, would be equal to, once again, the density of our fluid, H2O, times the gravitational constant. However, this time it's only a depth of small h multiplied by area. So the only difference between the force upward and the force downward is this big H. So we can write that the net pressure force is equal to the density of our fluid times G times big H, the height of our object, times A. So, if we look at this equation, we know that a height times an area, that gives us a volume times some density, that gives us a mass, and then a mass times a gravitational constant gives us the weight. So it will be equal to the weight of the fluid displaced. So our buoyant force is equal to the weight of fluid displaced. So, how does this extend to an arbitrary shaped object, for example, a human body? We can pretty much look at any object the same exact way. We would just have to cut it up into rectangles. So say I had some object of arbitrary shape, and we would kind of think of it as putting it through a French fry cutter, and we'll make differential rectangles throughout this, each having a height of h and a cross sectional area of a, and we would add all these up, all of our rectangles of our arbitrary shape, and we would once again get a volume, and we could multiply that by the density of our fluid times the gravitational constant to once again get the weight of fluid displaced. And that is how, using a force balance on a rectangular prism, the buoyant force is equal to the weight of the fluid displaced, and how it extends to an arbitrary shaped object.